All right, this is lesson 3 for fields. We're going to talk about charged plates and the Millikan oil drop experiment. So in this diagram here, we have two charged parallel plates. We have a positive plate and we have a negative plate. The electric field lines are pointing away from the positive towards the negative, which was actually what we talked about in lesson 1. Okay, electric field lines start on the positive and they move to the negative. There is a slight bulge at each end of the plate. That's just how it is. So the direction of the electric field is down. Okay. In the region between these plates, our electric field lines are parallel. So they're running in the same direction, right? Parallel are beside each other. And they are evenly spaced, which means the field is of equal magnitude at all points. So the electric field is in the same magnitude, same direction at all points. If we place a positive point charge between the plates, the net force will be the same direction as the field lines. So if we put a positive point charge between the plates, the net force is going to be in the same direction as the electric field because, of course, the positive point charge is going to want to move away from the positive toward the negative. So they're going to be going in the same direction. Okay. The negative point charge, if we placed a negative point charge, it would move opposite to the electric field line. So if you placed a negative point, let's say we placed a negative Q, it's going to want to go in that direction. Okay, and then we have to decide what's stronger, the electric field, or we sometimes have to consider gravity, but we'll get there. So the force on the particle can be determined by our formula F equals Q times E. So on your formula sheet, this one right here, electric force is equal to charge times electric field strength. If the electric force is the only force, then that's also the net force. So sometimes the net force is the electric force. Okay? If it's not, I will tell you there is gravity acting or there is this acting. But sometimes the net force is the electric force. Okay? So let's look at an example of this. So if the electric field strength between the plates is 10 newtons per coulomb, so that's E, and the object has a charge of plus 2 coulombs and a mass of 4 times 10 to the negative 4 kilograms, we can find the acceleration. So in this case, the net force will be the electric force because there is no other force mentioned. So remember, net force is the total force acting. Sometimes we have to add a whole bunch of forces, but in this case, the only force is the electric force. So we could do this in 2 steps. You could solve for Fe and then solve for acceleration. Or what we could do is we could actually kind of combine these 2 formulas together. Now if this makes more sense for you to find Fe first and then recognize that Fnet really is Fe and then solve the second equation, you can do that. But what we can do is Fe is really Fnet, which is Q times E. We know that acceleration is Fnet over m. So what we do is we just replace Fnet with Q times E. So acceleration is equal to Q times E divided by m. Okay, now again, if you prefer to do this and then use your force in this formula, that's absolutely okay. But we often do look for shortcuts where possible in physics. So Q was +2, E was 10, mass is 4 times 10 to the negative 4 kilograms. So our acceleration will be 2 times 10 divided by 4 exponent negative 4, 50,000 meters per second squared. Okay? The last piece we need to consider is the direction. So because this charge is positive, thinking of our scenario, it's going to want to go towards the negative, or in this case, down. So this is up, this is down, it's going to want to go down. Or we could say towards the negative plate. Okay, both of those are perfectly acceptable. You could also put this in scientific notation if you wanted, 5.00 times 10 to the power of 4 meters per second squared. Up to you. All right, the direction of the acceleration would be the same, down. Okay, sorry, just went over that. If the charged plates were oriented in an up and down direction, the particle also experiences a force of gravity, and we know that gravity acts downwards. Okay, so let's revisit the example. The mass of that particle was really small. Okay, so if we wanted to find Fg, let's remember that Fg equals mg, which equals 4 times 10 to the negative 4 times 9.81 newtons per kilogram. See, we can never truly forget anything we learn in physics. 4 exponent negative 4 times 9.81. The force of gravity is really tiny. It's 0.0039, which is so small. So if we were truly going to consider both forces, F net would be gravity and electric field force. We found that other force to be Ooh, we never actually found it. Well, the electric force would just be force is equal to Q times E. The charge of that particle was 2. The electric field strength was 10 for a total force of 20 newtons. Okay? So if gravity was this, and our electric force is that, we have to add them together, and we see that the presence of gravity really doesn't change our answer, right? We would still end up with this just being 20 newtons down, okay? So you might think, well, we kind of forgot to consider gravity on that first page. When particles are super, super, super tiny, gravity is what we would say is negligible. So it's very small. It could also mean ignorable, right? We don't really care. It's so small, it doesn't change our answer, okay? Now, when we're talking about electrons, electrons are extremely small in mass, so it is important to take into account gravity. So small mass, smaller masses, it's more important. Wait, it's less important. Sorry, guys. Okay, talking about charge plates and kinematics, we're still kind of going with our same example. If that particle, let's remember its mass was 4 times 10 to the negative 4 kilograms, its acceleration was 50,000 meters per second squared. If that particle is going down for a brief period of time, 6 times 10 to the negative 6 seconds, could we find change in velocity? Well, we could. Remember from kinematics, this is our equation. We could solve for v. To solve for v, we have to get it by itself. We're left with v equals a times t, which is 50,000 meters per second squared, times 6 times 10 to the negative 6 seconds. 50,000 times 6 exponent negative 6 is 0.3 meters per second. And this would be down, right? Because we're still talking about that initial scenario when the object is moving down. Okay, so we can never really forget what we've learned in the past because you never know when it's going to come back up. Okay, the Millikan experiment. So at the beginning of the century, so we're talking 1900s, I believe, they started to investigate electricity and electric forces a little bit more. And they started to think of two specific questions. Is there a smallest unit of charge of which all other units are multiples? So is there like a basic unit of how much charge can exist? And if that exists, how much is it? So how many coulombs is like the smallest amount of charge you can have? So Robert Millikan, he performed a series of experiments to try to get answers to these questions. So he thinks that the elementary charge would be 1 electron. So if you can figure out the charge of 1 electron, that's like the basic, because we can't get smaller than an electron, right? So he assumed further that when you spray oil in little droplets or a fine mist from an atomizer, they become charged by friction, right, bumping up against each other, and some acquire an excess of electrons, and others would acquire a deficit or a shortage of electrons. So there was no way to know how many electrons were going to stick to oil because electrons, of course, are so small we can't even see them with a microscope. But he thought if he could measure the total charge, it would have to be a multiple of that base charge that existed. So he used a uniform electric field that was created between two parallel charged plates, and he charged the plates with batteries. So he could have a thin mist of oil enter the field, and he could change the voltage, right? He could adjust the batteries, and he was able to change the field strength and therefore change the force. So he was able to make it so that the strength of the electric force was equal and opposite to the gravity force. And when you have equal and opposite forces, we call that equilibrium. So if you have an equal upper and downer force acting on these particles, they would balance, or they'd be suspended, or they'd hang out kind of in midair. So let's look at this little diagram. Remember, when we drew our free body diagrams, the arrows represent the vectors, the magnitude of the vectors. So if they're equal and opposite, you have that particle at rest, okay? Because, of course, if you have a negative at the top this time and a positive at the bottom, the positive wants to move up, right? The electric force is up because plus and minus attract. That positive particle doesn't want to come to the positive plate, right? This is negative, this is positive. So in that first example on the first page, the positive plate was at the top and the negative is at the bottom. We've just switched it. So that positive is attracted to the negative, right? But it's also being pulled down by gravity. So if he could make them totally equal to each other, it would be balanced. So when an oil droplet is balanced, that means that electric force equals gravity force. We know that electric force is really Q times E. We know that gravity force is really M times G. So we have an equation, and he could solve for Q. Rearrange so that Q equals mg divided by E. So it was possible for Millikan to determine the electric field strength by knowing the voltage that he had in the batteries. That's grade 12 stuff. But when that field is turned off, the particle starts to fall because, of course, if there is no electric force, the only force is gravity, and the particle falls to the bottom. It would reach a terminal velocity. We touched on terminal velocity in dynamics, where it's like the maximum speed you can reach while falling. And air resistance is determined by the radius of a particle. So once the radius was determined, then the mass of the particle could be determined. And that would all happen due to density. Okay? So he was essentially able to measure the charge of a droplet. Okay? Crazy. You're not going to have to tell me this story again, I promise. So he repeated his experiment over and over and over again. He generated a long list of values, and he had a pattern. And this pattern was that all of the values were a multiple of some base small value, which is what they kind of hypothesized. Some of the droplets had this small value, but none had less. So he didn't get any numbers smaller than this one particular value. So basically, current modern values have replicated his values almost exactly. So the currently accepted value for the elementary charge, or the smallest possible charge that can exist, is this number. It's very, very, very small. There are 18 zeros ahead of that 1. In our calculations, we are going to use this, 1.602 times 10 to the negative 19. So the charge is equal to however many multiples you have of this elementary charge. Okay, so Q is the charge in coulombs, E is the elementary charge in coulombs, and then N is just the whole number multiple, no units. Okay? So if the total charge on an object is 1 coulomb, it's possible to determine the number of elementary charges. The number is what we are looking for. Q is going to be 1. E is going to be 1.602 times 10 to the negative 19. Okay? So we're going to solve for N. We're going to divide both sides by 1.602. And we end up with N equals 6.25 times 10 to the power of 18 electrons. So what this is that's how many electrons are inside of 1 coulomb of charge. Okay? So, how many electrons are in 0.6 coulombs? Well, how many? That's going to be N. Q, our elementary charge, is this. Sorry. That's our elementary charge. And then Q is how many coulombs we actually have. So we're going to solve for N again. Now if you prefer to rearrange for N first, we can do that. So N equals Q divided by E, which is 0.60 coulombs, divided by 1.602 times 10 to the negative 19 coulombs per electron, you end up with 0.6 divided by 1.602 exponent negative 19. So 3.75 times 10 to the power of 18 electrons. Okay? How many coulombs are in a mole of electrons? This is for you chem folks. How many coulombs? We are looking for Q. Our elementary charge is this, and a mole. Well, how much is a mole? Avogadro's number. So we are able to solve for Q. N times E, 6.022 times 1023 times 1.602 newtons per coulombs per electron. We get 96,472 coulombs of charge in a mole of electrons. Okay, one more note is a proton technically has this as a charge, whereas an electron technically has this as a charge, right? Protons are positive, electrons are negative. The elementary charge is the same. One is positive, one is negative. Awesome, thanks for watching.